this video we're going to talk about solubility equilibrium. In this type of equilibrium, we have still a dynamic equilibrium that is caused when we have hydrated cations and anions in solution. And so what that means is we have some ions which have formed, which means some of the solid has dissolved, but some of the solid has not. And typically most of the solid has not. And so these are equilibriums that are established for the compounds we've previously called insoluble. The equilibrium constant is called the Ksp. Sp for solubility product is no more than the product of the ions that are in solution. And remember, our solids don't appear. So in this instance here, with the silver chloride breaking up into silver ions and chloride ions, our solubility product expression will be Ksp equals the silver ion concentration times the chloride ion concentration. Okay? And in your textbook, table 15.4, there is a list of common salts and their respective Ksp values. So, in this example here, we're going to write the Ksps for these equilibrium situations. So for the first one, we have our calcium fluoride, and so that's going to be calcium ions times fluoride ions, and this time that's going to be squared since there are two fluoride ions. Right, and so the next one would be our silver ions, again squared because there's two of those, the coefficient's 2, times our sulfate ion concentration. And the same for the last. We have our bismuth ions, which are squared since there's 2 of them, times our sulfide ions, which are 2 to the third since there's 3 of those. And so that's the same as before, and again we don't include the solids in our equilibrium expressions. Alright, so we can determine the solubility, or the Ksp in this problem, from our experimental values, just like we've done in the past. Okay? So in this example here, it led to chloride dissolves to a slight extent in water according to this equation. Calculate the Ksp if the lead ion concentration has been found to be 1.6 times 10 to the minus 2. So what we're going to do is we're going to let the lead ion concentration be x, and then our chloride would of course be 2x. So we would look at this as our in our ice charts. Right? So before we added our water, again our solid doesn't matter, before we would add our water we'd have no ions present at all. Right? Our change would then be that when we add the water, as it would shift slightly to the right, we would have plus x and then plus 2x. So at equilibrium we'd have x amount of lead ions and 2x amount of chloride ions. Right? And so again, it said that there was that our x was going to be 1.62 times 10 to the minus 2, and so that would be our x, and then our chloride ions would be 2 times 1.6 times 10 to the minus 2. And then we would plug that into our Ksp expression, which would be our lead ions, and then our chloride ion concentration squared. So our Ksp here would be 1.62 times 10 to the minus 2 times 2 times 1.62 times 10 to the minus 2 squared. And then so when we solve that, we would get 70 times 10 to the minus 5 will be our Ksp. Okay? And so then if we look at this next problem, I realize now I did the sample in the exercise 1. So let's look at our exercise 1. Right? This time we have copper 1 bromide. Alright, so if we write out the dissolution of copper 1 bromide, we would have copper ions and bromide ions. Right? Now here it tells us our molar solubility. Again, molar solubility is telling us our value of x, how much of our ion has dissolved. Okay? And calculate the Ksp value. again, if you think about our ice charts, we start with none of our ions to begin with. We add our water, our equilibrium forms, and we would have plus x and plus x. And so at equilibrium, we would have x amount of each. Okay, and so then our Ksp expression will be copper ion times the bromide ion, both to the first power since they're each one. And so then we could plug in, and sometimes you'll see the Ksp expression written in such a way that they plug x into the concentration, so x times x, and that Ksp becomes x squared. And so then our value of Ksp would be our molar solubility, 2.0 times 10 to the minus 4, which is our x squared. Right? And so then we would get 4 times 10 to the minus 8 for our Ksp value. Right, so that's calculating Ksp from our molar solubility values. Okay. Then we have our next problem. We have our calculator Ksp values for the bismuth sulfide, which has molar solubility. So again, that's our x. Okay. And then we're going to write our equilibrium expression. And we have 2 Bi plus 3s plus 3s minus 2s, right? And so again, our ice chart, or solid, doesn't matter. We start off with no ions. We're then going to form 2 x ions of bismuth and 3 times x ions of sulfide. And so that would be 2x and 3x, right? And so then our Ksp is going to be our bismuth squared times our sulfide to the third. And again, our concentrations are our x values, so x squared times x to the third gives us x to the fifth. 2x squared and 3x to the third. I apologize. And that gives us 4x squared times 27x to the third. Right? And we can plug x in to these if we want, or we can further simplify and then plug x in. You're going to get the same value either way. And you should get the 1.1 times 10 to the minus 73. And again, this means that the amount of product, the number of ions, the concentration of the ions here is extremely small in comparison to how much solid there is. So this is very insoluble. So the smaller this number is, the less soluble the substance is. Alright, so next we can calculate solubility from our Ksp, right? So that's what we're going to do in these next problems. Our relative solubilities can be deduced by comparing the values of Ksp. We do have to be careful because we can't just make direct comparisons with the Ksp values and the solubility, because remember, x is what we call our solubility. So we have to be careful when we talk about solubility, which is more soluble than the other. Okay. So let's look at this next example. The Ksp value is provided for us this time, right? We want to calculate the solubility. Again, that's asking you to find x. So let's write our this solution. We have copper 2 iodate goes to copper plus 2, and then 2 iodate ions. And so then at equilibrium, in our ice chart, we would have none to begin with. We would have plus x and plus 2x here. So at equilibrium, we have x and 2x. Our Ksp expression would be our copper plus 2 times our iodate squared. And so then we plug in our equilibrium values. Ksp equals x times 2x squared. If we reduce that, we would get x times 4x squared, so it would be 4x to the third. And again, we're looking for solubility, which is x. So how do we find x? Well, they gave us Ksp, So we plug that in. 1.4 times 10 to the minus 7 equals 4x to the third. So then we would solve for x. So we divide by 4. And then we get x to the third. So then we would take the cube root of both sides. Right? So when we take the cube root, so we have 1.4 times 10 to the minus 7 divided by 4. And then I would take the cube root of that. And there's several ways you can do that. You can raise it to the 1/3 power. You can go into your math and find the cube root either way. And so then we get that x would be equal to, right, this one was 3.5 times 10 to the minus 8 here. And then x would be equal to 0.00327. Now again, x is a concentration, it's a solubility, right? And that's what it is that we got here too. Just written in scientific notation. And the two significant figures, because that's what our K value was given to us in two significant figures. Alright, so then what happens when we have what we call the common ion effect? You kind of saw this in the Le Chatelier's principles lab, right? We've talked about common ions with Le Chatelier's principle. What happens when we add more of one ion? So in the example, if we have this, we saw that milk of magnesia activity, right? And so if we add more hydroxide, right, the sodium hydroxide that you added, right, then you would saw that this concentration increased, so it shifts back to the left. So that's what we're looking at here. How does that then affect the solubility, right? Now, if we add hydroxide ions and it shifts to the left, then we would expect that it would be more on the reactant side. You'd have more solid, making it less soluble, right? Because more ions would equal more solubility. All right. So in this one, it says calculate your solubility. Remember, that's X. Of our solid calcium fluoride has a Ksp of 4 times 10 to the minus 11 and a 0.025 molar sodium fluoride solution. So let's see how that affects what our ice chart looks like. So we start with our equilibrium reaction. So we have our calcium ions plus our 2 fluoride ions. So since we're adding this solid to a solution that already exists, that means that we have some of this ion already, right? So how much of this ion do we have? Well, since there's one of it, right, it's a 1-to-1 ratio, it would be 0.025 molar. We didn't have any of this in our solution to begin with. So we have our solution of our sodium fluoride. So if you imagine a beaker here that has our sodium ions and our fluoride ions floating around. And then we're going to take a spoon full of some calcium fluoride and we're going to dump that into there, right? That's what it's talking about that's happening. So we don't have any calcium ions to begin with. Once that hits the water, some of that will dissolve, right? And we'll call that X amount. And then some of our fluoride ions are also going to dissolve, and we'll call that 2X amount, again, because they're coefficient, right? So what happens then when this hits this solution? Some of those calcium ions do dissolve, right? And fluoride ions do dissolve, but when some of those calcium ions that do dissolve interact with that fluoride ion, they're going to form a precipitate, right? And so that's how we get a reduction in our solubility. So let's see by how much. So we have X, and then here we're going to have 0.025 plus 2X. Okay? And so we write equilibrium expression, Ksp equals the calcium ions times our fluoride ions squared. And so then we plug in our Ksp, 4 times 10 to the minus 11, equals X times 0.025 plus 2X squared. Now again, here's probably where you're going to want to use your solver again, right? And so we'll plug that into our solver to help us solve it. So we're going to have our X. So 0.025 plus 2X and then squared. Those we use in the old old-fashioned calculators like me, this has to be in parentheses, and then we'd have to say minus 4 times 10 to the minus 11. If we have to set that equal to 0. And then we hit enter, and then x equals 0, and then alpha solve. And so then we find that x is equal to 6.4, and it's going to be more than that, times 10 to the minus 8. So you want to make sure that you arrow all the way over when you get that x equals, because it's not 6.4, because you didn't even have that much to start with, right? There's a times 10 to something at the end, so just scroll all the way to the end. And that tells us what our solubility is now. Okay? So the only difference with the common ion is that we don't start with 0 here. Everything else works the same way. Right? We've already talked about Q. How does Q relate to KSP? Right? Same kind of way. If Q is less than KSP, we're not at equilibrium and it's unsaturated. Right? And so since Q is less than, to get to a saturated point, we're going to have to increase our product. So it would shift to the right and it would dissolve more, become more saturated. If Q is equal to KSP, then that's at equilibrium. That's considered to be saturated. If Q is greater than KSP, then the system's again not at equilibrium. That's what we would call supersaturated, in which case it would shift to the left, right? And that's when we get our precipitates to form. Okay. And this would be precipitate formation. All right, so let's look at some example problems here. So in this example here, we're talking about a solution that is prepared by adding 750 milliliters of 4 times 10 to minus 3 molar cerium 3 nitrate and 300 milliliters of 2 times 10 to minus 2 molar potassium iodate. Will the cerium precipitate in this solution? Right, so again, in order for the precipitate to form, what we just said, right, is that we would need that the Q would have to be greater than the KSP, right? And so our KSP is this, so Q would have to be greater than 1.9 times 10 to the minus 10 to form a precipitate. Okay? So let's see if we get a precipitate to form. So again, let's think about what's happening. We have a beaker and a beaker, right? In this beaker we have our potassium and we have our iodate, and in this beaker over here we have our cerium and we have our nitrate, right? And we're going to pour one into the other, right? And have a precipitation reaction. So if we have a precipitate reaction, we're going to be precipitating cerium iodate. So if we write that equilibrium situation, we'd have cerium plus 3 iodate ions, right? So we need to be able to calculate Q, so we need this initial condition. So what are the concentrations of these two things when we add them together? So the iodate came from the potassium iodate, right? And it had a concentration, or 300 milliliters of 2 molar, 2 times 10 to the minus 2 molar solution. So, I'm sorry, that was the cerium. Oh no, that's iodate. Okay. So our iodate concentration, right, is going to be how many moles of iodate this would be, right? So to find those moles, we would take our 300 milliliters times our molarity times 10 to the minus 2, right? But then we're going to divide that by the total volume because we're adding two solutions together. So our total volume are going to be these two added together. It's going to be our total volume, right? Because they're not staying separate, right? So our concentrations will change based on that. So our total volume here would be 1,050 milliliters. Now, since I kept them both in milliliters, that would cancel out. So this is kind of like a dilution problem, right? So that would give us our concentration of iodate. So that would be 300 times 2 times minus 2, divided by 1050. And so our iodate concentration will be 0.00571 molar. And we do the same thing for our cerium. Right? And so we start off with 750 milliliters of a 4 times 10 to the minus 3 molar. Again, that's a 1-to-1. There's one cerium in that. And then divide by our total volume again of 1050. So 750 times 4 is 10 to the minus 3 divided by 1050 gives us a concentration of 0.00289 molar. So now we know our initial concentrations. Again, these are initial concentrations. Right? We can plug those in and solve for Q. So what would be our expression for Q? Right? We have cerium to the first, and we'd have iodate to the third. Right? So now we know our concentrations. Cerium is 0.00289. Our iodate was 0.0057, but that's going to be to the third. And so then we calculate Q. So we multiply 0.00289 times 0.0057 to the third. And then we get a value of Q that is 5.35 times 10 to the minus 10. Now again, we said that Q had to be greater than K, right? So 5.35 times 10 to the minus 10 is larger than 1.9 times 10 to the minus 10, and so yes, we do get a precipitate because Q is greater than K. Okay. Alright, I'm going to let you do exercise 6 on your own. You can have the answers down here at the bottom. Okay, let's see what you can come up with those. And tomorrow we will look at going over that if you have questions.